All right, let's go ahead and get it started. My name is Praveen Rokaya. Today, on behalf of core modeling leads, Professors Al Petronero and Martin Clark, I'm pleased to welcome you all to the annual meeting of the Global Water Futures Core Modeling and Forecasting team. Before we begin, I want to acknowledge that the University of Saskatchewan is located on Treaty 6 territory and the homeland of the Métis. Just a few housekeeping information before we formally start the program. I will be checking any questions through the chat function today. In this Zoom meeting format, the Q&A button is not available. So please send your questions through the chat. Please also turn off your audio and video unless you are speaking, at least for the first 1 hour of the program. Also, the first 1 hour of the meeting today will be recorded and made available afterwards in Core Modeling website and Global Water Future YouTube channel. So please stay tuned. This is all for housekeeping. Now I would like to request Professor John Pomeroy, the Director of the Global Water Futures Program, to give us some overview on the Global Water Futures vision for modeling and prediction. John, the floor is yours.
Good morning, and thank you, Pravin. So I wanted to talk a bit about where we are with GWF, and then also some important news for the core modeling team that I think you'll probably like. So I'll start by sharing my screen, and hopefully there. Right. So hopefully you can see things now.
Yes.
Wonderful. Want to remind everyone, as we always have to, what our mission is now that we are well into the program. So we're to find solutions to water threats in an area of global change with three main elements which resound very strongly with the core modeling team. One is to improve disaster warning. And so, of course, your prediction and forecasting elements of core modeling are crucial for that. The second is to predict water futures. These are longer-term predictions. And so really the rest of the modeling team fits in that area. And then there's also informing users and helping them adapt to change and manage risks. And of course, the tools that are created under core modeling are crucial to that element as well. So core modeling is important to all of the aspects of the Global Water Futures mission, which is no surprise because it is the largest single entity funded by Global Water Futures. You're larger than any of the projects, and you have more people, you have more funding, and you have greater expectations on what you'll produce as well. So that's one thing to keep in mind. And core modeling has a dual role. So one aspect, of course, is working in developing the models and working, making sure that the projects and others internally to GWF have access to models and to the data they need to run these models and apply them. But there's also an element of users, which has been less well developed for core modeling. But I think now you're getting greater user engagement. And through linking with the IMPC project, which is strongly transdisciplinary, you also have access to further user needs and engagement. But remember, GWF is a transdisciplinary project, and that means that the users are involved in all aspects of the program from its beginning to end, and they have been. So that's a very important part of what we're doing. We have a users advisory committee, which met yesterday. And it was fascinating because on there was a fellow named Hank Venema, who heads a company based in Winnipeg, consulting firm. And he's been doing modeling using our models to run further models more tied to user needs in the Red and the Assiniboine River Basin, and just saying how useful the models are for what he's doing. But also people like that can add tremendous value to what we're doing. And by linking to in areas such as southern Manitoba, which has terrifically difficult and challenging water management problems. So that user link is really important, and they can add tremendous value to what we have. So I want to remind the core modeling team to keep that in there and be very open to working with users as you move forward. Also, realize that the core modeling is part of a family of core teams that together couple water observations, data management, water prediction, and knowledge mobilization. And this, again, is extremely important for GWF to have these all linked together. And this is how you can accomplish those links to users through the KM team. But also then access the data from the 60 observatories that are across the country in most of our prediction basins, and that by using the data management system that we have. So also critically important to this is an enabling group, the computer science group, which has been working on, of course, integrated with model development, particularly with next generation modeling, but also with visualization tools that they're developing. And this is another way to link to the users, but then also getting their help in finding ways to bring the data and information into the models in the first place is crucially important. And those research basins, remember, they have absolutely crucial data for you to test your models, to benchmark your models, to develop improved algorithms, and to make sure you're close to reality. And so that's just one of the 60 there. Internationally, I want to remind you of the Planetary Water Prediction Initiative, which is closely tied to and really managed within the core modeling theme. This involves user engagement and sometimes high-level engagement. There's going to be a meeting later this month with the foreign ministers of Russia, Tajikistan, Pakistan, and Nepal, and that I'll be speaking at about some of the issues that we have. But the big thing that we can bring to the table are the advanced models we have. And so we focused on cold regions around the world with an initial and particular emphasis on those that originate in high altitudes. And so we have model development going on right now in northern India and the Upper Ganga Basin, and in Central Asia as well. And we will be moving very quickly now to developing these in the Andes, in South America, and other model development and testing in the Pyrenees in Europe and other regions. And but this is these are just beachheads for really continental scale modeling that envisions really the whole world, including the northward flowing rivers. But we have a tremendous number of international collaborators which can help us with this, but we've got to do the work, and so we're ramping up that effort now. Now, we had a wonderful annual general meeting back in May. It was online, but with parallel sessions. There was lots of modeling in there. And a few things struck Professor Schuster-Wallace and myself about where GWF is at right now. And we noted that with the scientific underpinning and new code and computer developments, we have these fundamental modeling and prediction systems that can do the things that we wanted them to: disaster warning from floods and droughts, water quality degradation. But now is the time to integrate and implement these models. And we've made great progress in diagnosing different dimensions of changing water futures, and we built models that predict these changes. But now is the time to synthesize our assessment of water futures and deploy these models to predict change and impacts on the environment, people, and economy. And so I'm raising the human element of this, which has not been so much evident in core modeling to date, but will be, because we've also had a midterm review of the program. And the midterm review had many elements that they looked at. There were not complaints over the core modeling. They saw that as a strength of the program, and that's really good. But they saw elements of GWF that needed to further develop. And this is great because, in fact, it was in our plans to further develop these aspects. One is human water systems, and the other is water and health components of GWF. And so the review panel wants to see enhancement of that. And so we've been developing an action plan, which will be discussed at the Strategic Management Committee this afternoon, And one of the aspects is reallocation of funds to core modeling team, which I'll be proposing to the SMC. So I'll tell you what we're talking about. One is to establish a human water benchmarking working group in core modeling. This would be supported by one PDF with a policy governance expertise. And it would, that person do literature reviews, stakeholder synthesis, so tying into the users on some core human water indicators, but then build an indicator system that will enable benchmarking performance for governance deficiencies, policy transfer, and social learning. So we're particularly concerned where water misgovernance or deficiencies are occurring in Canada, and can we diagnose these with some of the core models. And so large emphasis will be on the more heavily managed rivers, river systems and basins across the country, and ones with high population zones. So you can imagine the Saskatchewan Nelson, the Columbia, the Great Lakes, St. Lawrence being areas there where governance deficiencies and issues and needs for policy transfer might be heavily apparent. And Canada has binational relationship with the United States, particularly on the Great Lakes and on the Columbia, which are coming to a head in terms of negotiations. So this is something of importance. The second is to establish a health working group in core modeling to advance predictions of mosquito-borne diseases. This is something that some land surface models have been able to do in the past, but we think with a model such as MESH or perhaps some of the next gen models, we can do a really spectacular job. And these are diseases carried by mosquitoes such as West Nile, which is very prevalent during drought, or Zika, which has already entered into bits of southern Ontario. And of course, with climate warming, we can see more tropical diseases spreading in Canada. So this would be an epidemiology background PDF to help with this. And we would couple the hydrological models with vector-borne disease models, and then run these under different climate scenario developments for Canada. So that would certainly get a lot of interest, I think. And then the third element is socio-cultural flood and drought vulnerability. And as a way to look at climate change resilience using hydrological model prediction. And this would be bringing in a PDF with water knowledge and social science methods expertise to develop flood and drought predictions constrained by identified vulnerability domains. So what's that? Well, what it means is that, let's say your model predicts a high flow for Winnipeg. We'll just pick on Winnipeg for example. What does that mean? Does it mean a flood? Does it mean a little bit of water in the basement? Does it mean they have to operate the spillway? Does it mean lots of water in the basement? And 2 inches of water in your basement versus having your basement filled with water have vastly different impacts on people's lives. And so we want to make sure that we have these impacts and we can constrain some of the model predictions by these vulnerability domains where groups are vulnerable. And so that's so that would be the third one. So basically, reallocation of 3 postdocs into core modeling. Dr. Corin Schuster-Wallace would be involved with some of this, along with others that will be identified. So wrapping up, where are we at now with GWF? Well, we worked with over 450 users to develop a variety of transdisciplinary solutions to manage water-related risk in a wide variety of sectors across the country, agriculture and industry and hydroelectricity and energy, other energy sources, manufacturing, others. Now we need to share, evaluate, compare, and contrast those solutions, define those of which most suited the purpose, and work with our users to implement them in institutionalized, solution-based, equitable, inclusive, and evidence-informed approaches to achieving water sustainability. So I hope that's through development of a Canada Water Agency that might be able to take on some of the core modeling. 2 of the major political parties are now supporting the concept of the Canada Water Agency, so knock on wood. And a third political party has promised to institute a national flood forecasting and drought forecasting system. So, so there's great hope that whoever forms the government after September 20th will be interested in some of the things that core modeling produces. And of course, working with our international partners to make sure we're providing global water solutions around the world. So I'll wrap it up there and wish you the best. I'll be watching all of this and of course involved with the next generation aspect. So thank you so much.
Thank you, John. That was very insightful to hear a high-level perspective from you. I will definitely work towards integrating more human dimension aspects moving forward. Now we'll be moving towards the keynote talk of today. It is my pleasure to introduce Professor Mark Perkins, who will be presenting on advances in large domain hydrological modeling at Utrecht University, global hydrology, global groundwater, and mountain hydrology. Professor Perkins holds the chair in Earth surface hydrology at the Department of Physical Geography at Utrecht University. His field of expertise are groundwater hydrology, ecohydrology, stochastic hydrology, hydrological regionalization, upscaling theory, and geostatistics and global hydrology. His current research focuses on global scale hydrological modeling in relation to climate change and water availability. Professor Perkins is a fellow of the American Geophysical Union and editor of Water Resources Research Journal. He was supervisor to 26 completed PhD theses and has been a committee member on more than 90 PhD theses. He has also contributed to about 225 publications, more than 185 of which appear in international peer-reviewed journals. Professor Perkins is a principal author of the book Upscaling and Downscaling Method for Environmental Research, published in 2002, co-author of the book Sampling for Natural Resource Monitoring, published in 2006, and editor of the book Climate and Hydrological Cycle, published in 2008. Professor Perkins, we are very pleased to have you here, and the floor is yours.
Thank you, Praveen. It's an honor to be speaking here for such a strong modeling group. Let me try to share the screen if I can do that. Hopefully I can.
Yeah.
Is this visible right now?
Yes, not in PowerPoint.
Okay, now I have to get it into presentation mode. Here it is. Okay. So what I'm going to do is tell you a little bit about what we have been up to.
We can't see the PowerPoint. We can see Finder window.
Yeah.
Oh, you can't see the PowerPoint.
It's the wrong window.
Yeah.
Okay, so I have to unshare. Let me see what happens. Stop share. Ugh. Ah, here it is. Maybe that's the correct one.
Yes.
Yep, that's perfect.
Yeah, that's it. All right, good.
Thanks.
Okay. So in this presentation, I'm going to give a short overview of what we have been working on in the last couple of years regarding trying to understand the terrestrial global hydrological cycle, in particular the impact of man on the hydrological cycle. And you can do that in many ways, remote sensing, many in situ observations, but we are mostly into large scale or continental to global scale modeling. There's actually three, I would like to start a little bit by explaining or introducing or reiterating for some of you our in-house global hydrology and water resources model, PCA-GLOB. And some recent advances in there, and then also focused then on what are sort of niche-ish compared to other large-scale modeling groups is focusing on large-scale groundwater modeling. Since I was asked to also tell something about well, physical geography, most notably Walter Immel's group, and I've been a part of that work as well in the earlier parts, since he was part of my group before. Is the hydrocryosphere modeling in high mountain Asia, which relates a lot to what has been going on here. And then actually recently we have a project where large-scale groundwater modeling and hydrocryosphere modeling comes together into one particular pet project that we've been working on. And I would like to show you some early results of that. So that's sort of the outline. So starting with the global hydrology model, PCA-GLOB, it tries to simulate terrestrial hydrology at 5 arc-minute resolution with daily time steps. different than many of the global hydrological models, but akin to what was done in, for instance, HO8 and water gap, two other of similar models. We try to integrate fully the what humans do in the water cycle. So we simulate every time step what the water demand is. We try to estimate what the water demand is of the different sectors. And then that results in a water withdrawal from either groundwater or surface water or reservoirs, which is then leads to a water consumption. So part of the water is evaporated and return flows to either surface water or groundwater. So that's integrated at time step. We also include non-conventional water sources like desal. And we also have a couple of, about 8,000 reservoirs in there from the Grant database that are placed at time step in time as they appear as they are being built. So this is just an overview of the different sectors that we consider here. We look at irrigation, which is of course the main water user, but also industrial and domestic water use, where industrial water use consists of both cooling water and manufactured water use, and of course livestock, which is only a small part in many parts of the world. So like I said, the reservoirs that we have, they are actually, if we do a reanalysis of the terrestrial hydrological cycle of the last, say, for 50, 60 years, we basically place the reservoirs at the time they have been built in the model, and then also let the reservoirs fill up. So we have really the transient effect of the reservoir building in time. So that's something that we include as well. This is important because reservoir filling can be a problem downstream while the reservoir fills up. Now, there's apart from the PCA Glob proper, there are a number of extensions that we have been working on and developing that are coupled to a PCA Glob or are post-processing to PCA Glob. One is the global groundwater model. We have a 5 arc-minute global 2-layer groundwater model. This is work of Inge de Graaf mostly. That can be coupled one way. So we just run first PCA Glob and then the output, which is recharge and or net recharge and surface water levels, and we use that as boundary conditions to a groundwater model, which is based on mod flow. But we can also fully couple or dynamically couple it, where these things are exchanged every time step. Then there's the dynamic water temperature model by Nico Wanders that allows us to also simulate water temperature over time, again at 5 arc-minutes. And another tool that we have is called GlowFrim, where we can actually couple different types of routing models. So we have our own very simple routing in PCA Glob and also a simple inundation model, but we can also couple 1D routing and even a code, in this case Delft3D, but we can also ListFlood FM that solve the full shallow water equations, and also you can have these backwater effects included. So this is an application where all the 3 types of models are used in one simulation run, coupled using BMI, which is to some of you, of course, like Martin, who coming from NCAR, is well known as a coupler between models. So some applications of the model, we've been using it apart from scientific, answering science questions, also in what we call water and climate services. For instance, here on the lower left, we have the Aqueduct Water Risk Atlas by the WRI, the World Resources Institute, that is basically based on simulations with our model. And we're also currently working on future water risk indicators based on projections from CMIC6. Related to that is the floods, the aqueduct floods, where you can actually work out what the current and future flood hazard and risk is going to be, and how you can reduce economically flood risk by building flood defenses. And there's another one related to that, but then on the water scarcity side is the water to invest tool, which allows one to assess for a water province, which is a cross of an administrative and a hydrological border or entity. For these water provinces, you can assess what the future water stress is going to be, or water gap actually for all the sectors together, and then also select certain measures and see how much dollars it will cost to close the water gap, and if it can be closed at all. And then finally, there's also more the operational things. We're also working on different seasonal forecasting initiatives, mostly paid for by the Copernicus CS3 program, to set up seasonal forecasting systems, mostly over Europe. So what are the last developments that we're working on? So the more black this line is, the more advanced it is. So we're changing this water quality model, DINWAT, that now only has temperature, to a full quality model that has nutrients and BOD and fecal coliform, for instance, in it, chloride. We're also trying to incorporate an energy balance and richness equation for the soil, which is very experimental still. There's the first, we've done the first simulations for the Rhine Basin with that. We would like to incorporate crop growth. We're currently starting with some EU projects where this is going to be implemented. And we have a BMI coupling now recently between ModFlow 6 and PCA Glob, because we're going to build our new global ModFlow or groundwater models in ModFlow 6. Now, we also try to move to 1 kilometer globally, but that is going to be, that's an issue, especially with the routing. So we also have plans also in a big ERC project that we acquired to apply recent technology, which is called asynchronous many-task technology, to put that into the Python PCA raster scripting language to make PCA Glob much faster and enable us to simulate at 1 kilometer in the end. And we already have a 1 kilometer version of ModFlow that I can see, will show you in a minute. So this is an example of the steady state simulation with the 1 kilometer ModFlow model, which is based on ModFlow 6. It's basically based on smart decomposition of the terrestrial surface into subdomains, and these subdomains and then optimizing the linear solvers, the multiple linear solutions that are needed to solve the whole system. And we've been now able to do some also transient runs. So this is 1 kilometer closely. So if we run 50 years, it takes now about 16 hours on about 1,000 cores to run 50 years, but this is a monthly time step, not daily. And for groundwater, actually, it turns out that monthly time steps are okay-ish. I would like to go to a week to do it better, but for now, this is where we are at. Moving to the groundwater a little bit more, what we've been doing, we are also interested not only in groundwater quantity, but also in quality, and mostly looking at deltas and coastal areas. This is work from a PhD that got his degree last year, Yuri van Engelen, trying to explain the salinity distribution in the Nile Delta. This is the Nile Delta with some observations of salinity at different depths, and you can see that there's quite some saline water, shallow saline water at the northern part of the Delta, and trying to explain that. Yuri made a paleogeographic reconstruction of that particular delta, which you need to do to understand how salt groundwater is distributed. So it turned out that the coastal area during the so-called fast Holocene transgression was much more back, was about 70 kilometers inland compared to now. So that explains these saline observations, and there were also saline inland lakes or lagoons there 1,000 years later that explained that basically led to convection and groundwater salinization. And what Yuri did is using a CWAT model, which is MT3D and ModFlow coupled. Also a parallel version of that to simulate over one glacial cycle the evolution of the salinity in that delta. Now, he did that also for about 15 other big deltas, using, of course, in this case, a more schematized setup of the delta. And the final sort of end piece of his work that he's still working on actually is trying to see what happens in the future with these deltas on the socio-economic and climate change in terms of groundwater salinity and salinization of pumping wells, for instance. Now, another PhD does that, not looking at deltas, but at the coast, mostly consolidated sediments. And what you can see here is that what they did is basically make these simulate likely sediment setup of the coastal based on a coastal typology, and then make in this case coastal models, CWAT models, simulating over one full glacial cycle how salinity developed over time. And what you can see is that if you that you have quite large quantities of fresh groundwater still offshore. This is the current shore, because there are capping clay layers that were exposed to very long times of recharge during a low stand, and now still contain fresh water that can actually be exploited. And in this study, this volume of fresh water, offshore fresh water, was estimated and also contrasted with the onshore water demand. And turns out that in certain areas of very high onshore water demand, even close to the coast, there's huge amounts of even shallow fresh groundwater below the continental shelf that may be as a backstop, used as a backstop in a transformation to more sustainable water use in the future. Now, the other thing that he looked at is the effect of sea level rise on salinization of coastal freshwater resources. So this is onshore, and this shows you the decline in volume of onshore fresh groundwater under an 8.5 scenario around 2100. Now, moving now to Walter Immel's group. This is Walter Immel here. He's actually working mostly on, he has done a lot of work in the Hindu-Kush Himalayan, a lot of modeling work there in that region. But he's not only modeling, he's also doing lots of field work. So he has two experimental catchments, one close to Mount Everest, and the one that he has worked on the most is the Langtan Valley, which is about 100 kilometers north of Kathmandu. This is Walter here. And there's a huge amount of instrumentation there. This is just examples. They have these robust, high elevation, 5,000 meter weather station, automatic weather stations. They have the even eddy covariance towers that they put on top of clean ice and debris covered glaciers. This is some drone work. They were the first to fly drones at that altitude to map elevation and surface temperatures. And this is a snow sensor based on gamma ray, where you measure a snow water equivalent in the surroundings. I had the pleasure to go on 2 expeditions with these guys, and it's really, well, you know, many of you know how hard work it is to get that stuff up there and install it. Anyway, it's very important to upscale the insights from the small scale into these large scale models and to make large scale predictions. And that is what Walter is doing. He built this model called SPY, which is actually built on the same with the same programming scripting language, PC Raster Python, as PC Glob actually. Difference is that PC Glob focuses on human impact, and SPY has spent a lot of work on modeling the more cryosphere type of processes. So snow modeling, but also glacier modeling, and glacier dynamics are an integral part of that model. So the total runoff from a cell is the surface runoff, lateral flow from the soils. There's also permafrost in there if possible. Base flow if there's groundwater available. Recharge of the groundwater from the soil and the glaciers itself, but also glacier runoff and snow runoff. Moving into a simple lake and reservoir scheme to get discharge. Just some examples of the modeling there. This is a study of Arthur Lutz a couple of years back, where for the Hindu Kush Himalaya, he assessed using a version of SPY with remote sensing, parallelized with the remote sensing data and some of the smaller scale observations from the pilot basins, the contribution of the different runoff components, and of course you see the impact of the very large glaciers here close to the Karakoram, lots of glacier runoff here, and of course in the Himalaya much more important, especially the eastern Himalayas, of monsoon rainfall. Now he did the same then looking at the changes thereof under climate change. These are just different climate scenarios, a dry and a cold scenario, dry, warm, wet, cold, and wet and warm. And then you can see, especially in the wet and cold, there's huge the dry and warm. There's huge changes in a reduction in snow and glacier runoff that is actually replaced by more monsoonal rainfall, making sure that the discharge into the 20th century from all of these basins more or less remains constant. Only the timing, of course, is going to be different, and you can see that in the next one. You can see that this shows you the increase and decrease of the timing of discharge. So if it's red, you get less discharge than under the current climate, and if it's blue, you get more discharge. There are certain basins in the Kush Himalaya that are showing an increase in discharge throughout, or a decrease in discharge throughout, but there are real changes in timing, like here. The green and red one here shows you how accurate these results are. So the red blobs, there's lots of differences between the this basically is the coefficient of variation between climate models. So they run multiple climate models for a given scenario. Okay, then moving to the last set of slides. So we've looked at the groundwater, we've looked at the mountain hydrology modeling, and here in this little project, we bring it together. We got some seed funding to answer the question, what typically is done in IPCC assessments and so on, that glacier runoff is directly moved into the ocean with the idea that everything that all excess melts, so all the mass imbalance ends up in the ocean. Now we were asking ourselves, is that really the case? And we tried to do a model study where we use PCA Glob ModFlow, a dynamically coupled version of it. So we have you see it on the upper right here. You see a piece of the ModFlow model of the Indus Basin. And this is the outline of the basin that we considered. So we have a surface water groundwater model simulating hydrology, and that was coupled with basically fed with a glacier model. So we took the Randolph Glacier inventory to mask out the glaciers from PCA Glob. Those areas in those cells, those areas were basically the runoff generated in those areas in the cells from PCA Glob was taken out and replaced by a glacier model runoff from Philip Kraaienbrink. He has a dynamic glacier model that can run through all these thousands of glaciers across the whole Himalaya. And we use that one for the output for that. And he ran, first of all, a current simulation based on observations of of meteorological forcing, which is the era 5 bias corrected over the period 1979 and 2019. Of course, you have a mass imbalance currently, but he also made a version where he has a mass balance, not for a given year, but across the whole, 40-year period. There is net mass balance across those glaciers. And then he increased the mass imbalance in the subsequent runs. And then we run basically PCR glob with these different cases, with glaciers with a full mass balance and glaciers with increasingly more imbalance between accumulation and melt, representing a warmer climate. And then we looked what the difference in runoff and evaporation between the run with the glaciers in full balance and with the imbalance runs, and looking at the excess discharge and the excess evaporation there. And that is what you see here. This is the increase in discharge due to the mass imbalance. This is for the current mass imbalance, by the way. This is the change in total evaporation. So this is this is the difference between the situation with and without, or without mass balance minus the situation with a mass balance. And you can see actually that, and we're looking here at the excess runoff. So that's basically the amount of runoff that is generated, and you can see that it's not too big, but it is significant. This is the excess evaporation, the total evaporation. You can see that most of that evaporation is basically goes into that excess evaporation goes into excess surface water irrigation. So the evaporation from that, you can actually see that because of the because there's more surface water available. That's what our irrigation scheme basically prescribes. It looks for how much water is available in the different sources. Now, if there's more surface water available from more discharge, then the groundwater irrigation actually reduces. And you can see that in this area, because of more excess surface water, groundwater pumping is reduced, and therefore also the evaporation. Now, if you then look at the cumulative excess loss, you can see that, of course, so that's what goes, so that's basically what comes in from the glacier additionally from the mass imbalance, and what then ends up in the ocean. You see that there's less, suppose there's a 10% increase in discharge upstream, there's only maybe 8% of increase in discharge downstream. So that's the excess loss. So that's the Q excess in from the glaciers minus the Q excess out. And you can see that that there's indeed some of the, not all of the water that is created in excess due to glacial melt ends up in the ocean. Now, where does it go and how much is it? Well, actually, it's not that much. It's on average only 4%, but so 96% on average of that excess melt due to the glacial imbalance finally does end up in the ocean, in the Indus here. You can see that, but that ratio that is changing rapidly between one year and the other, because in certain dry years it can up to go up to 20%. But there are also minus areas where more water is actually less water is flowing in than flowing out, and that has to do with you know, that we're looking here at years and not hydrological years. Maybe that's something we should change, which means that you got a legacy of excess downstream groundwater and reservoir storage that's released in cool, wet years that you can see. And then finally, where does it go? Most of that excess loss, well, most of it goes into the evaporation, right? So only little goes into the groundwater storage, And so additional groundwater storage. If you have more discharge, you also need a little bit more storage, right? If you also have increased base flow. But most of it goes into the evaporation and mostly into the surface water evaporation. And you can see that the groundwater evaporation even reduces because in some areas it gets less because of more surface water availability. Now the excess melt does have a big impact actually on groundwater recharge. But if you look at the groundwater depletion that heavily occurs in this area, it's actually hardly impacted by the excess groundwater recharge and the reduced groundwater pumping in some areas. Because in many of the other areas, that recharge is mostly occurring in areas where from the rivers, because the excess discharge of the glaciers comes from the rivers, infiltrates upstream and then discharges again downstream as runoff again, as discharge. So it doesn't, it's not picked up by the areas with large groundwater overexploitation because there is little surface water available. So also that excess recharge is not felt there. So it's quite a complicated story here, but at least we see that the assumption that most of the glacier runoff ends up in the ocean sort of seems to be okay, because you know, if we include also the uncertainties here, it's within the noise that is retained for irrigation evaporation here. Another interesting thing, that's my last slide, has to do with the reservoir storage. I think that's a more compelling story. You can actually see this is the Tabela reservoir, which is handling a lot of the huge discharge volumes from the huge glaciers of the Karakoram. And if you get more imbalance, you can see that actually it increases the inflow in the reservoirs by close to 80%. So that's huge. But it also, because of the larger inflows, you, of course, assuming that the downstream demands do not change in this case, you can see that you're allowed to have a much more constant water storage and a much more robust system because of that. Obviously, this is temporary because once you go over peak discharge, which is in the Karakoram around 2070, of course, the discharge from the glaciers start to decrease again. So this is a more hopeful picture than it seems. So with that, I would like to end this talk. Thank you.
Thank you, Mark, for such a fascinating talk and taking your time to present at our annual meeting, particularly considering it is late after hours work time. If you have any questions for Mark, please send them in chat. I already see a few questions in the chat, so it would be great, Mark, if you could stay a little bit while and respond to some of these questions. Now we'll be moving towards next presentation. It's my pleasure to welcome Professor Martin Clark, who is a co-lead of the core modeling and forecasting team, along with Professor Al Petronero. He'll be presenting us on major science advances made by the core modeling and forecasting team. Martin, the floor is yours.
Okay, great. And thanks, Mark, for that great presentation. I'm wondering, Mark, if you can stop sharing your screen so I can begin sharing mine. Perfect, thanks. It's coming up slowly. Okay, here we are. Can you see the correct screen?
Yes.
Okay, great. Okay, well, thanks. I'm giving this presentation on behalf of Al Petronero, Praveen, and the core modeling team. It's going to be a quick flyby of some of the major advances that we've made over the past couple of years. So we can get started. John mentioned in his presentation at the beginning that Global Water Futures is all about solutions to water threats in an era of global change. The objective is to place Canada as a global leader in water science for cold regions and to address the strategic needs of the Canadian economy in adapting to change and managing the risks of uncertain water futures and extreme events. We're here in the core modelling program. Al and I are co-leading that program, supported by Praveen, who does a lot of the heavy lifting to keep everybody together and on track. As you're aware, we've got a number of themes. I'm going to be going through these in the presentation. Spatial meteorological data, led by Julie Thoreau. Geospatial intelligence, by myself. Current generation hydrological modelling, led by Bruce Davison. Next generation hydrological modelling, led by John Pomeroy. Water quality modelling, led by Philippe Van Capellen. Water resources modelling, led by Trish Stadnick. Hydroeconomics by Roy Brower. And hydrological forecasting by Al Petronero. And I think everyone's aware we've got 31 faculty, 33 research personnel, primarily postdocs, and 21 collaborators. So to start going through the spatial meteorological forcing data, had a few advances over the past couple of years. Key advance has been the work that Go-Chung Tang has been doing in developing spatial meteorological data sets. Over North America, Go-Chung developed SCDNA, which is the serially complete data for North America. And then EMDNA, which is the ensemble meteorological data set for North America, providing multiple realizations of spatial meteorological fields to characterize uncertainty and model inputs for hydrological models. Go-Chung, under the Planetary Water Prediction Initiative, also extended those globally. He developed SC Earth, a serially complete data set for planet Earth, and EM Earth, which is the ensemble meteorological data set for planet Earth. There's also been a lot of work on evaluating satellite products for Western Canada. The regional climate model simulation outputs are ongoing. The CONUS 2 simulations are coming along nicely now. The historical period is completed and the future run should be ready by early 2022. So these are the WRF simulations that Yanping Li is leading. Also some progress on the GEM simulations over Western Canada. This is the work that Julie Thoreau has been leading. And a lot of recent progress on downscaling CMIP6 precipitation and temperature products by Simon Papalaxio. If we move to geospatial intelligence, I think this overlaps with a lot of the work that Mark was just presenting. We see here that hydrological models have got common requirements for DM analysis, parameter inference, etc., but different models use different tools. So we're trying to push forward a model agnostic philosophy so that we can provide generalizable, publishable tools that are applicable to a wide class of different models. Some of the key work that's been going on here is the work by Wouter Knurben, who's been developing general model agnostic workflows to configure large domain hydrological models anywhere on the planet. Also the work by Shivan Gahari, developing EasyMore, which is a model agnostic approach for remapping of irregular data. A lot of work on process-based parameter inference across large regions. A lot of the work that started there has been primarily on sensitivity analysis, parameter sensitivity analysis. Some of the great work that's been coming out of the PKIP group, and then also some of the recent work that Hongli Liu has been doing as she's been joining us from NCAR on large domain parameter estimation, with her work starting with large domain sensitivity analysis. A lot of work also on developing benchmarking systems to be able to identify the weaknesses in our models. Al and Praveen have been making a lot of progress on using data from the research basins that John mentioned for model evaluation. We've published our paper on LAF tests for land models to identify kind of like the entry-level requirements that we must meet for land modeling capabilities, and beginning to pivot to some of the large domain model benchmarking efforts. The paper that I'm mentioning here on the bottom right is one that just came out in Water Resources Research, which is looking at the sampling uncertainty and some of the performance metrics that are commonly used in hydrological models. So here we applied the results to about 670 basins across a large domain. And the tolerance interval, 90% tolerance interval, is about 0.1 for many basins, meaning that we really need to be very, very careful when we're looking at small differences in the KGE and NSE statistics that are commonly used for model evaluation. The current generation hydrological modelling, this is a project that's the theme that's led by Bruce Davison. A lot of progress on the St. John and the publication submitted there. The model benchmarking runs are well underway for some of the really big basins across Canada, Mackenzie, Saskatchewan, Yukon and Fraser. Model benchmarking runs are underway for the Great Lakes. A lot of process improvements as well that are necessary to apply these large domain models across Canada, improving glacier representation, improving water management and irrigation algorithms, a lot of work from Fuad there. Major advance recently has been developing a vector-based version of MESH, which simplifies the application and improves the physical realism of the application across large domains. And then some work that I'll touch on a little bit later that John mentioned, some of the modelling of the international basins in high mountain Asia using MESH. In next generation hydrological modelling, this is the theme that's led by John Pomeroy. A lot of the work has been based on the Canadian hydrological model, and the key paper from that is Chris Marsh's paper that came out in 2020, G&D. The initial version of the Canadian hydrological model has primarily been focused on snow processes, and a lot of the work that's going on now has been what we call colloquially putting the H into CHM is to extend the CHM infrastructure to simulate the wide variety of hydrological processes from the top of the canopy to the bottom of the bedrock and from summit to sea. So a lot of the other models that we have are being integrated into CHM, some of the work that we're doing with SUMA, and in the future, some groundwater models, which interfaces with some of the work that Mark was talking about, and some of our river routing models, such as Miseroute. The software engineering approach there is a hierarchical coupler, where we want to couple model components at different levels of granularity, where we can include different capabilities at the equation level, as well as larger model building blocks, such as an entire snow model, an entire soil model, etc. The water quality modelling, a lot going on there. The simulations of soil and snowpack processes, stream temperature, sediment transport, coupled hydrology, biogeochemistry, etc. You can read what's here faster than I can talk about it. Some major outcomes, advances in modelling soil winter processes, integrating a wide range of different models, focus on nutrient legacies, cold region lakes, etc. And a lot of the advances in future directions here can be discussed in more detail in the water quality breakout group. This is led by Philippe Van Capellen. And water resources modelling, led by Trish Stadnick, and the primary goals are applying existing integrated water management modelling frameworks and integrating water management rules and land and hydrology models. The main work packages is the first has been to embed lakes and reservoirs into land models. This is the work that's being led by Sivan Gahari. So what he's done has he's been building on the recent publication of Miseroute version 2, which is a global application that includes parallelization of hierarchical river networks. He's been incorporating lakes and reservoirs into that model. A lot of work with Andrew Teffs on incorporating additional reservoir management models into large domain hydrological models, and Andrew Teffs and Sivan have been working very, very closely there. A key focus here is to understand seasonal ice effect rating curves and incorporate those into water resources management models. And the key themes that are coming up here, and as these are coming up across a lot of our research themes, is that the work must be model agnostic. We want modules that can be applied across many different hydrological models, be able to be applied across the continental domain, be computationally efficient, and be open. A lot of the water resource models are proprietary, and as we're moving to the application of water management principles and earth system models, we need to adopt the fair practices that the models be findable, accessible, interoperable, and reusable. And then carefully benchmarked so that we understand the model capabilities and the areas that need improvement. Hydroeconomics, this is the work that's led by Roy Brower. Main objective is developing integrated hydroeconomic modelling tools to assess the broader direct and indirect economic impacts of water policy under climate change. This is a pretty small team that's working on that, but the publications that are listed at the bottom here have been pretty impressive, and a large number of really important accomplishments that will be fleshed out in the hydroeconomics breakout group. Hydrological forecasting. This is the theme that's led by Al Petrodero. So a number of research foci. First is system development for flow guidance. So developing systems to couple and schedule forecasting components, model spin-up, data assimilation, downscaling, NWP output, forecast runs, etc. So there's two main outcomes there. The first is the work that's being led by Mohammed El-Shami, which is the cloud-based quasi-operational flow forecasting system prototype in the Yukon River Basin. This has been a pretty impressive accomplishment. No forecasting system really existed there, and they were able to provide a tool to address an unmet need in a very, very difficult and challenging part of the country to simulate hydrological processes. Also in system development, the work by Louise Arnall in implementing the SHARP system for Canadian basins. The other focus here is hydrological forecasting development. So a lot of work led by Karl-Erik Lindenschmidt on developing and operationalizing riverized modules for mesh. And then a lot of work that's beginning, it's not listed here, on hydrological data assimilation. This is the focus of the PhD by Dave Casson. In terms of the hydrological prediction test beds, I mentioned the data dashboards. That's in the geospatial intelligence section. That's a key part of test bed development. Louise Arnall has been developing a hydrological test bed for Nival basins across Canada, and looking at the relative importance of data-driven and mechanistic modelling approaches there. Also with Louise, as she's made advances in understanding what we call the elasticity of predictability, understanding that hydrological predictability stems from our knowledge of hydrological initial conditions as well as the future weather during the forecast period, understanding the relative importance of hydrological and meteorological predictability, and understanding the elasticity of predictability, where we understand how streamflow predictions can improve if we're able to provide improvements in estimates of the basin initial conditions and that meteorological forecasts, and understanding how the relative importance of hydrological and meteorological predictability varies with forecast initialization time, forecast lead time, location, etc., can help us guide a lot of science investments. Underlying all of this is a key accomplishment in hydrological forecasting is that GWF hosted the second Canadian Flood Forecasting Symposium that brought together a lot of the work, other operational work on hydrological prediction for the provinces and territories across Canada, as well as a lot of the research advances. And this work's evolving in close collaboration with Environment Canada's hydrological prediction effort. Key linkages with some of the key groups in Environment Canada there. John mentioned the Planetary Water Prediction Initiative. So the goals there are really twofold. Excuse me. The first is to build computational infrastructure to enable state-of-the-art hydrological simulations anywhere on the planet. So that's a lot of the work to improve the global data sets on climate forcing. Mentioned Go Chung's work, DEMs, we're doing a lot of work on global hydrography, which is beginning to come out, and veg soil, etc., which overlaps with Wouter's work. And using these data to configure hydrological models for the global domain. And then the second thrust there builds on the hydrological infrastructure, the computational infrastructure that's been developed, and developing regional models in key areas where GWF has got strong collaborations. So a lot of work in high mountain Asia at the moment, some work beginning in the Andes to begin to address those. And those regional models leverage, the computational infrastructure that's being built more generally. So to summarize, if we kind of have a colloquial description as to what we're doing, it's computational infrastructure to enable large domain hydrological modeling with deterministic and probabilistic forecasting capabilities. A lot of our philosophy is model agnostic, where we're focusing on community hydrological modeling rather than developing a community hydrological model. We're interested in developing a community of practice to more effectively share code and concepts across different model development groups. And in general, developing state-of-the-art capabilities and predicting terrestrial water energy and biogeochemical cycles. So pause there and stop sharing my screen. And we can move on to the subsequent aspects of the program.
Thank you, Martin. That was a great summary.